use is straightforward. We'll use the company by sector table for this example. Let's assume we want to list every company with a stock price greater than 1,000. Since we only want to include a certain subset of the companies, we use a where clause. We will set the numeric filter to show the companies where the stock price is greater than 1,000. As a result of the query execution, we receive a subset of data with the list of companies that satisfy our filter settings. Filtering based on character strings works in similar ways. Now let's generate a list of companies which belong to the information technology sector. We create a new filter where the sector column values should be equal to information technology. Now the query execution results window has all companies belonging to the information technology sector. Now we can combine the two filters. Composite filters are quite common. Sometimes, where clauses can be the longest part of a select statement because there are so many conditions that need to be satisfied. To filter for rows that satisfy both conditions, we use the AND keyword. For example, we want to find companies from the information technology sector with a stock price greater than 1,000. For that, we combine the two filters we previously created. The query results show two rows which represent one company, Alphabet, that owns Google. The two tickers are the result of the stock split in 2014. Now, if we want at least one of the conditions to be met, but maybe not both, then we can use the OR keyword. In our filter, we change the AND to OR, execute the statement, and observe that there are two companies in our data set which are not in the information technology sector. Let's stop here and talk about code formatting. You probably noticed that we started using left indent in the query strings. There is no single rule for styling the code. However, we think it is a good practice using indents in complex queries. SQL is a programming language. As with any other language, you may like to take an extra effort to improve readability of your queries. This will pay off later when you will start editing and debugging your code. Now let's move on to the character filters. In SQL, the like operator is used to determine whether a character string matches a specified pattern. A pattern can include regular characters and wildcard characters. There are many options for working with the like operator. Before we show the example, we want to explain what the term wildcard character means. Wildcard character is a special symbol which can stand for a certain range of characters. Here is the table of wildcard characters used with the like operator. The most used wildcard character is the % symbol. It represents any string from an empty space to a string with any number of characters. For example, if we wanted to find all companies with the abbreviation Inc. in the name, then we should construct the following filter. With that, we include companies that have a comma after the Inc. string. Note that we added a space in front of the Inc. to distinguish the abbreviation from Incorporated from an accidental case where the company can have Inc. characters inside the title. If we add not to the like operator, then we can filter companies with the names that do not have Inc. in their names. We need to mention that you have to be careful when using % at the beginning of a string. When this happens, the database cannot use indexes that may be on the column. This will cause the database to scan every row in the table looking for matches. It will still work, but might take longer time than you expect. Another example of using like operator with the % wildcard is to list companies whose names start with A. We can create composite filter and list companies whose names start with A or B. For that, we can use two filters with a % symbol which start with A and B. We can also use the square bracket wildcard to construct the same filter. If we want to list companies with the names that do not start with A or B, we can use not like operator or square brackets with the caret. If for some reason you are looking for companies with 6 letters in the title, you can use the like operator with 6 underscore wildcards. Alternatively, you can use the len function that returns length of the string. Query with the filter where length of the string is set to 6. This will return the same results as the query with the underscores, but is more readable. Subqueries. We usually select data directly from tables and views, but sometimes we might need to get data from the results of another select statement. We can do this using SQL subqueries. Subqueries can be used in 3 different parts of a select statement: in the select values list, in the from clause, and in the where clause. Let's work through an example of each of these 3. At first, we will introduce concept of prefix. Since we have multiple select statements within a single query, we'll want to make sure the database can tell which table each value comes from. To do this, we will use a table alias and include that alias as a prefix for each value we will return. In our example, the table company by sector has alias T1. So all columns retrieved from the table T1 has to have the prefix T1. Now we will create a subquery that will calculate average stock price by sector. For that, we will use the same table, company by sector, but with a different alias. We will call it T2. We add a restriction that we are interested in the average by sector, and the sector names in the table T1 and T2 should match each other. In some sense, we are joining our table T1 with the list of calculated average values. We will look deeper at the join conditions when we study table joins. Let's look at the query one more time. Here we have the subquery that calculates the average stock price from the company by sector table, but only using rows where the sector name is equal to the sector of the company the algorithm is currently looking at. Note that we place the subquery where we would usually have a column name. We call the new column sector average. In the results table, we see that we have added an extra column, sector average. This column lists the average stock price for the corresponding sector. Let's look at another example of how to use subqueries in the from clause. At first, we construct the plain query for retrieving sector names and stock price values from the company by sector table. Now we want to know average stock price by sector, but we are only interested in companies with the stock price greater than 100. We can find this information by constructing a subquery in the from clause with the where filter. Basically, we will select from the results of another select statement. As before, we will add an alias T1 to name the results of the subquery. Here we add one more clause, group by, for explaining the SQL engine that we want to calculate average stock price by sector. The results table shows the list of sector names with the average stock price. Note that only the companies with the stock price greater than 100 were included in the average. You may notice that we did not use prefix in the column names. We did so to demonstrate that the SQL engine is smart enough to understand our needs. Here you may see that the results of the query with prefixes are the same as without. However, we recommend using prefixes for improved readability and debugging purposes. Prefixes are essential when you work with more complex queries. Another place where you can incorporate subqueries is the where clause of the select statement. These subqueries can be used when we want to make comparisons within a single table. For example, if we want to find the sector of a company with the highest stock price, we can use a subquery in the where clause. This subquery will find the maximum stock price in all sectors with the max function. Then we will use this maximum value in the filter to find the company sector name. Note that we used different aliases and prefixes T1 and T2 for each select statement. This query will work without aliases and prefixes. However, we recommend using it. Also, you might note that we used single spaces as the indents. Again, use of single or double space indents or not using indents at all is a matter of style. We intentionally vary indents along the examples to demonstrate various styles. You pick the one that works best for you. Combining Tables, Part 1. You might hear the term joining tables, which is a common operation in SQL. However, the range of commands that SQL Server has for combining tables is wider. We will cover joins, union, intersect, and except. Table joins is one of the key features of the structured query language. When working with data, we sometimes need to retrieve data from two or more tables. For that, SQL has several variations of join command: inner join, left, right, and full outer join, and cross join. Although the join commands work with tables, sometimes for illustration purposes, the tables are shown as circles. The inner join command, or the simple join, returns a table that has records which conform between table A and table B. Here we should say that in order to make the join possible, both tables should have similar columns. For example, table A has stock tickers and the stock prices, while the table B has stock tickers and company names. The joined table will have the list of stock prices and company names for cases where the rows in both tables have the same tickers. We will explain this statement when we show examples. The left outer join results in a table that has all rows of the left table, table A, and rows from table B, the right table, that match the join condition. The right outer join is the inverse of the left outer join. Actually, the words inner and outer are optional when it comes to the writing the commands. It's okay to skip it. You can write and say only join instead of the inner join, and left join or right join instead of left outer join or right outer join. The full outer join command produces a joined table that has all rows of table A and table B. The columns with unmatched rows in the resulting table are empty, or, better to say, are filled with the value of none. The cross-join command can be considered exotic. However, there are cases when it helps to reduce the amount of data manipulation actions. With the cross-join command, we can generate a data set where for each row in the table A, we will have all rows of table B. The following examples will clarify each of these join commands. In this example, we will demonstrate how to use the join commands. At first, we will create two tables in our S&P 500 database. For that, we will use the create table command. The new table, named Table A, Company Stock Prices, will have two columns, the column with tickers and the column with the stock prices. We will populate the table using insert command and insert values for tickers and stock prices in 4 rows. The insert command is used to add new rows to the table one by one. To add 4 rows, we need 4 insert statements. Now we will create another table named Table B Company Names with 2 columns, ticker and company name. We will add rows to this table in the same manner as before using 4 insert statements. The first 3 rows will contain the same tickers as in Table A. The last column will contain ticker that does not exist in the Table A. We made that to illustrate the difference in the join commands moving forward. Now let's select data from Table A and Table B and execute the 2 select statements in the same query batch bounded with the Go command. Note that 2 select statements in one query batch resulted in 2 tables in the output window. Also note that the 4th rows in both tables have different company tickers. Now we will give an example of the inner join command. This select statement will combine ticker, company name, and stock price columns from Table A and Table B. The join operation is performed on the column ticker. To differentiate the tables, we add prefixes TA and TB to the column names. The result of the inner join operation is a new table with 3 rows with ticker values, company names, and stock prices of those companies. The 4th rows in each table were skipped since the ticker values did not match each other. The keyword inner in the inner join command is optional. The same query will work in the same way without the inner keyword. Now let's examine the left outer join command. The select statement is similar to the inner join command that we created before, except now the join command is called left outer join. The resulting table has 4 rows. All data from the left table, here Table A, is included. However, the last row has the null value in the company name column. This happened because the right table, Table B, did not have information on the company name for the record with this ticker. It did not have such a ticker at all. To create the right outer join select statement, we need to replace the word left with the word right in the join command and change the prefix in front of the ticker column name. Now we need all data from the right Table B and only rows that match Table B ticker values from the Table A. Look at the resulting table. The last row has the null value in the stock price column. This happened because the left Table A does not have stock price data for this ticker. This is a mirror-like situation to the previous example. Note that if we did not change the prefix in front of the ticker column name and retrieved tickers from the left column A in our right join statement, then we would get the awkward results where the last row either did not have the ticker value or the stock price value. In the same way as the inner join statement works the same without the optional keyword inner, the outer joins work the same without the word outer. These keywords are used to ease reading of the SQL code. Now let's see what happens if we execute the full outer join command on the tables A and B. The full outer join command includes all rows of the table A and all rows of the table B. Since we join tables on the ticker column, we will get the table with all the ticker values. The rows that did not match tickers from both tables will have null values in the cells. Here, the 4th row has the null-valued cell in the company name column. The 5th row has the null in the stock price column. The last join operation we will consider here is the cross join. For that, we will create another table called Group Numbers with one column, Numbers. We will populate this table with 3 integer values using the insert command. With the select statement, we check that the new table is properly populated with the values 1, 2, 3. To construct the cross-join select statement, we will use the select statement we created for the inner join. We will select ticker, company names, and stock prices from the inner join select statement and cross-join it with the group number table with the only column number. As with all join statements, we will create aliases to the table names and add it as prefixes to the column names. The resulting table has the data in 3 sets of repeating rows. The ticker, company name, and stock price values came from the inner join of Table A and Table B. Each row in this inner join is then repeated for each row in the group number table. This is how the cross-join operator works. As a result, we tripled the table we get from the inner join. Sometimes you will need double or triple data sets in your data science work. For that, you can use the cross-join operator, which is quite handy. Combining tables. Part 2. In the previous section, we considered join operations. Joins used with filters can create almost any combination of tables. However, the join statements easily can become too complex to read and expensive for the server to execute. To simplify the code structure and to improve SQL Server performance, sometimes we can use union, intersect, and except commands. In contrast to the join command, these commands work only with rows. In other words, all data sets in these commands should have the same columns. To illustrate these commands, we will depict tables as circles and place the circles one below the other. The commands union, intersect, and except can merge the tables with equal columns, return the common rows, or subtract one table data from another. In the example section, we will show how each of these operators works. We will start with creating 2 tables in our database S&P 500. Both tables will have 2 columns, company name and stock price. We will fill the tables using the insert command and add 3 rows into each. The only difference in the 2 tables will be the last row. The last row in Table A will have a different company record from the last row in Table B. We will use 3 rows for the illustration purposes only. For the commands we will show, the number of rows in the tables can be different. With the 2 select statements, we will check if the tables were filled with the data as expected. The 2 select queries are executed in one batch, so the result window shows 2 outcomes simultaneously. This is convenient when you want to compare 2 data sets. Now we will take these 2 select statements and combine them with the union statement. As a result, we will get a table where all distinct rows from Table A and Table B are united into one data set. If we want to combine all rows from Table A and B, ignoring possible data repetition, then we can use the union all command. Note that the resulting table has the repeating rows. The reason is that part of the data in Table A also exists in Table B. Remember that we intentionally constructed the tables with the repeating data. To list the data that is common in both tables, we can use the intersect command. The select queries with the intersect will only return rows that exist in both Table A and Table B. Lastly, if we want to find rows in the Table A which are unique for this table and do not exist in Table B, we can use the except command. As you can see, these 3 commands, union, intersect, and except, are quite handy to use. Together with the join command, they form a powerful set of operators for combining tables. You will often meet these commands when you are working with views. Creating a view. Often, you will create complex queries that will join and filter data from one or more tables. If you will routinely use the results of such queries, we recommend creating a view. A view is a database instance that looks much like a data table, except that this is not a real table. It is, rather, a result of an SQL query. Before we start working on views, we will demonstrate a feature of the SQL Server called Query Execution Plan. At first, we will create a select query in our S&P 500 database. This query will use average function and list average stock prices in each business sector. The query will include only companies with stock prices greater than 100. Before we execute the query, let's take a look at the execution plan. For that, we should select the query of interest and click the Display Estimated Execution Plan at the menu bar or press the Ctrl+L key. The result window at the bottom will show a scheme. The sequence shows the execution plan for the select query. Below each icon, the SQL Server Management Studio shows estimated time in percent of executing each operation or the cost of the operation. This functionality will be especially useful if you will be working with large data sets and complex queries. Knowing the estimated execution plan, data practitioners can rewrite the query and make it more cost-effective. However, we showed the estimation plan for another reason. Now, let's execute the query, ensure that it generates the result we expected, and create a view from this query. We will use the Create View command and name the view Top Sector Average. To see the list of the views in your database, we can expand the database tree in the Object Explorer window and find the branch named Views. Now let's write a query for retrieving all data from this view and see its estimated execution plan. For that, we select the query and click on the Display Estimated Execution Plan button. Note that the estimated execution plan for this simple query is exactly the same as for the source query we used to create the view. The reason is the nature of views. Views are not real tables, but rather virtual tables. When we created the view, no data were copied or moved. The data still exists in the same table. We only created an alias for the query. Now let's delete this view with the drop view command and create another one. Although the views are virtual tables, the importance of views for some applications like data warehouse is so high that the question of data retrieval performance becomes increasingly important. In this query, we select several columns from the source table and apply the filter. The resulting dataset has unique ticker values in each row. Now, we will create a view from this query and then create an index for this view. Indices can improve the query performance and, as a result, improve performance of views. We will call this view Incorporated, since it will let us view only the companies with the abbreviation Inc. in the name. Since we know that we are going to create an index for this view, we will bind this view to our schema called DBO. For that, we will use the keyword schema binding in the create view command and place the source table name in the square brackets with the database schema as the prefix. Let's select all data from this view to ensure that it is all set. Now we can create the index. We will use the create index command with the keywords unique and clustered. The first index for the view has to be clustered index. We will create the index on the column ticker in the view named Incorporated. The new index will be stored in the database under the same schema as the view. Now, all select operations with the indexed view will perform much faster than the query we used as the source for the view. You will note the performance improvement when you are working with large data sets. To delete the index, we can use the drop index command. Note that we should indicate the name of the view as the prefix for the index name. Finally, we can delete the view using the drop view command. Deleting the view is not the same as deleting the table. After the view is deleted, all our data will remain safe and untouched. Grouping and ordering. Grouping and ordering data sets is very easy with SQL. Let's see how this can be done on the examples. With the clause order by stock price, we can order the results by the stock price in ascending order. If we want to be explicit, which is always recommended, we can add a keyword ASC to indicate the sorting goes in ascending order. We can order the records by the stock price in descending order by using the keyword DESC in the order by clause. SQL can also sort by string variables. For example, we can sort our data set by the company name. With the keyword DESC, the sorting will be in reverse alphabetical order. The first rows in the resulting data set will have company names which start with the letter Z. Use of an ASC keyword will sort the results in regular alphabetical order from A to Z. In SQL, grouping is also straightforward. In this query, we will calculate average stock price by sector. For that, we will use the group by clause with the sector variable. One thing we should mention here is that the select statement should only have the variable that you are using in the group by clause. In other words, if you will try to select sector variable and the company name from the table, the query will generate an error since the company name variable is not in the group by clause. Lastly, we will show how to perform filtering on the grouping results. For that, we will use the having clause. The having clause is like the where clause we use in filters, except the having clause can filter the results of grouping. Here, the query will return the list of business sectors and the average company stock prices in each sector sorted in ascending order. Note that because of the having filter, the resulting set includes only stock prices greater than 100. Partitioning. One of the greatest things that SQL can do with the data is automatically creating subsets of data and performing calculations on it. The function that can create subsets or partitions of data is called partitioning. The command that tells SQL to perform calculations over the subsets is called the keyword over. Combined, the function is called over partitioning. We will demonstrate how to calculate average on the subset of data. Count the number of records in the subset, calculate rank of the record, show the row number, and split the data into a fixed number of subsets or tiles. Before we start, we will recall how we calculated average in our previous examples. For that, we used the average function with the group by clause. The limitation for this query structure is restriction on the list of columns in the select query. We cannot list other table columns in the query like this. The overPartition function removed this limitation. We can construct a query with the list of the table columns, calculate average stock price in each sector, and display it as the calculated column. This query tells the SQL server that we want to calculate average stock price on the data set partitioned by the sector variable. The records with the same value as the sector variable will form a separate data subset or partition. Now we will count how many companies are in each sector. For that, we will use the count function with the over partition clause. Note that we use the keyword distinct to avoid repetition. Since SQL attempts to show the count values for each company name in the table, we do not need this. We also want to sort the results by the number of companies in each sector in descending order. For that, we use the order by clause with DESC abbreviation. Next, we will calculate rank of each company in each sector by its stock price. The SQL function rank will serve our needs. The following query tells SQL Server to partition the data set by the sector variable values, sort the companies in each sector by the value of the stock price, and assign a corresponding rank to each record. The company with the lowest stock price in the sector will have the rank of 1. The following company with slightly higher stock price will have the rank of 2, and so on. The highest rank will have the company with the highest stock price in the sector. If the two companies have the same stock price, then they will have equal ranks. In a similar table, we can generate replacing the rank function with the row number function. In this query, the companies are sorted by the stock price values in each partition. The row number function returns the place of the record in the partition. The difference with the rank function is that if the two companies have the same stock price values, then its row numbers will be different, while the rank functions will return equal values. SQL has a function called entile. This function can split the data set into a fixed number of subsets. The number of subsets is the integer argument of the entile function. Sometimes you may need to split your data into several bins or tiles. For that, you can use the entile function with the partition clause. In this example, we will split companies in each sector into 4 subsets or 4 tiles. As you can see, the 4 subsets has seemingly equal number of records with each sector. However, this is not exactly so. The entile function does not always split the records into the equally sized tiles. They are about the same, but not strictly equal. Unfortunately, we cannot control the exact number of records in each tile with the entile function. That is why we recommend checking the size of each subset before using the results. To see the actual size of each file, we can create one more query on top of the query with the entile. In this complex query, we will select data from the partitioned dataset and count the number of companies in each tile. As we can see from the query results, the entile function split the dataset into about equal tiles, but not of the same size. Use the entile function with caution. Date and time, Part 1. We talked about how to work with numeric and character data formats. With SQL, it was relatively simple. However, when it comes to data and time, there is no single recipe. The challenge is in variety of possible data formats. In your work, you may meet date records in various styles and languages. We will show you how to import the date and time records into the SQL tables and deal with the variety of styles. SQL has 2 main data types to work with date and time. These data formats are called date and time. Very natural. But we recommend importing your date and time records as strings. After that, you can attempt to recognize the correct date and time format and convert the strings to date and time data types. For the data type conversion, the SQL Server has several functions. The cast function is the most common SQL function. With cast, you can convert between all major SQL data types: numeric, character, and dates. The convert function is similar to cast. The only major difference is that with convert, you can specify the style of the date format when converting from strings to dates. Most likely, you will never need the style option in your data science work. Parse is the most advanced function for converting strings to dates. It can understand most date formats. Be aware that parse is not a native SQL function. You have to have a .NET framework installed on your machine to make the parse function work. Parse is a function of the Microsoft .NET platform that you can seamlessly run on your SQL server. If your servers are remote, then quite possibly the parse function will not work. So use parse with caution if your SQL scripts will work in a production environment. The three more functions, try cast, try convert, and try parse, are the same as cast, convert, and parse, except that it will not throw errors if the conversion will fail. Instead, these try versions of the function will silently return null values and will not stop the SQL execution. To demonstrate how to convert strings to the date format, we will create a table in our S&P 500 database. The table will have only one column in varchar data type. We will populate the column with strings containing dates in various formats. Let's check that the table is populated with the data as expected. Now we construct a select query with three functions, try cast, try convert, and try parse. These functions will attempt to convert our records into the date format. After the query is executed, we can examine the results of conversion of each function. We can see that the try-cast and try-convert functions performed equally successfully and failed on the same records. The try-parse function did the better job. It managed to convert all records to the date format correctly, except the last one. Fortunately, the parse function has an option to change the date regional settings, or culture, in the terms of the .NET framework. In the new select query, we will indicate that the records should be treated as if it came from Finland. For that, we set the try parse to use the Finnish style of date recording. As we see from the resulting table, the try parse function correctly recognized the last record and converted it to the date format. However, now it does not recognize some dates recorded in a format that is not used in Finland. In your data science work, you may need to vary regions and converting functions to enable correct date conversion. To help you with that, we included culture codes for various languages that you can use with the using command in the parse and try parse functions. If you will be using the parse function a lot, you will notice that it is not as fast as other SQL functions. Part of the reason is that parse is not a native SQL function. To improve performance, you can copy your select statement results into a new table. With that, you will have to convert dates only once, and then just retrieve the converted data from the table you created. You can create a new table with the select into command. The command is much like the standard select statement, except that you indicate a name of a new table where you want to copy the results of the query. The SQL server will automatically create the table and copy the results. Selecting from the new table will be much faster. You will notice the performance improvement when you will be working with large data sets. Date and time, Part 2. As you saw, converting date and time is not something that can always be done with a routine procedure. Now we will introduce one more converting function that is native to the date and time formatting called datepart. But we will not stop here. We will move one step ahead and explain how string functions like ltrim, substring, and concat can help when all-over conversion functions fail. To start, we will create a table with a string column and fill it with time records in the string format. As we said before, we recommend you start working with date and time records with the string format and then convert it into date and time. The string records that we insert have 3 sets of numbers, each separated with a colon. It stands for hours, minutes, and dates. We intentionally placed leading and trailing spaces around the digits. In real-life records, we will meet all kinds of formats and obstacles. Now we will convert the string records into time format with the try_parse function. As you see from the resulting table, the parsing function did its job well and converted the strings into the time format. With the datepart function, we can extract information about hours, minutes, and seconds. For that, we will apply the datepart function to the results of conversion and use the appropriate keywords, hour, minute, and second. The result of this query is a table with 3 columns that contain information about hours, minutes, and seconds. There are more keywords that you can use with the datepart function to get even deeper insight into the date and time records. So, we successfully extracted the information on time from our string records. But what if the parse function fails or is not available? We will show you how you can parse the string with the means of the SQL string functions. At first, we will use the ltrim function to cut out the leading spaces in our records. If we would like to cut out trailing spaces, then we use the rtrim function. Since we know that our records have 3 sets of digits divided with a colon, and each set stands for hours, minutes, and seconds, we can extract these 3 parts with the substring function and call it hours, minutes, and seconds in the string format. The substring function takes 3 arguments: the name of the string variable, the starting position of the substring, and the length of the substring. We can see from the resulting table that our string parsing process works. Now let's create the true time variable from the results of our string parsing efforts. At first, we will concatenate the strings with information about hours, minutes, and seconds. But the concatenated string should also have a colon as the separator. That will help to convert it to the time format. So we construct a nested query where we get the inputs to the concat function from the previously created select query. Finally, we need to convert the concatenated string into the time format. We can do that with the convert function. As we can see from the query result, the conversion was a success. Now you know how to convert your date and time records into the date and time format and use it in your data analysis work.